close your eyes and imagine floating peacefully in the vast darkness of space. We're going to take a gentle journey through our solar system, discovering its wonders one by one. Let your mind drift as we explore. Our story begins 4.6 billion years ago, in a quiet corner of the Milky Way galaxy. Where you might expect to find emptiness, there was instead a massive cloud, a nebula of gas and dust, spinning slowly in the cosmic void. This cloud was enormous, stretching across billions of miles, composed mostly of hydrogen and helium left over from earlier generations of stars that had lived and died long before. Something happened to disturb this peaceful cloud. Perhaps a nearby star exploded in a supernova, sending shockwaves rippling through space. Whatever the trigger, this disturbance caused the cloud to begin collapsing in on itself, pulled together by its own gravity. As it collapsed, it began to spin faster and faster, like a figure skater pulling in their arms during a pirouette. Over millions of years, this spinning cloud flattened into a disk shape, with most of the material falling toward the center. At the heart of this swirling disk, where the pressure and temperature grew intense beyond imagination, something remarkable ignited. When the temperature reached about 10 million degrees Celsius, hydrogen atoms began fusing together to form helium, and our sun was born. In that moment of fusion, our star began to shine, containing 99.86% of all the mass in what would become our solar system. Everything else, all the planets, moons, asteroids, and comets you've ever heard of, makes up less than 1/7 of 1% of our solar system's total mass. The young sun was turbulent and active, more violent than the steady star we see today. Its powerful solar wind, streams of charged particles flowing outward, began pushing the lighter gases like hydrogen and helium away from the inner regions of the disk. This cosmic wind would shape what types of planets could form where, creating an invisible line that would determine the destiny of worlds. While the sun stabilized at the center, something equally magical was happening in the disk around it. Tiny particles of dust, no bigger than grains of sand, began sticking together when they collided. These grew into pebbles, then boulders, then mountain-sized chunks of rock and ice called planetesimals. Through countless gentle collisions over millions of years, these planetesimals merged into larger and larger bodies. The solar system was beginning to take shape. As you drift deeper into relaxation, let's journey inward, closer to the warmth of our young Sunday. Here, in the inner solar system where temperatures soared, only the hardiest materials could survive, metals and rocks that could withstand the heat. The lighter elements had been swept away by the solar wind, leaving behind the ingredients for something special, the rocky planets. Mercury formed closest to the Sun, a world of extremes. This small, dense planet became the fastest orbiting world in our solar system, racing around the Sun once every 88 Earth days. Imagine, a single year on Mercury passes in less than 3 of our months. Yet despite this rapid orbit, Mercury rotates so slowly on its axis that one day on Mercury, from sunrise to sunrise, lasts 176 Earth days. This creates a strange ballet where Mercury completes 2 full orbits around the Sun in the time it takes to experience 3 Mercury days and nights. Moving outward, we find Venus, Earth's mysterious twin. Venus and Earth formed at roughly the same time and are nearly identical in size. Venus is only about 650 kilometers smaller in diameter than Earth. For this reason, Venus is often called Earth's sister planet. But this sisterhood took very different paths. Venus became shrouded in thick clouds of sulfuric acid, with an atmosphere so dense that the atmospheric pressure on its surface is 92 times greater than Earth's, equivalent to being 900 meters deep in Earth's oceans. This crushing atmosphere traps heat so effectively that Venus became the hottest planet in our solar system, with surface temperatures reaching 465 degrees Celsius, hot enough to melt lead. Then comes our home, Earth. The third planet from the Sun holds a distinction that makes it truly special. It's the only world we know of where liquid water exists in abundance on the surface. Approximately 71% of Earth's surface is covered by oceans, giving our planet its characteristic blue appearance from space. This water, combined with our planet's position in what scientists call the habitable zone, created the perfect conditions for something extraordinary, life. Earth is the only place in the universe where we know for certain that life exists. Beyond Earth lies Mars, the red planet that has captured human imagination for centuries. Mars gets its distinctive rusty color from iron oxide, essentially rust, covering much of its surface. This smaller world, about half the diameter of Earth, holds the tallest mountain in the entire solar system, Olympus Mons. This massive shield volcano rises 21 kilometers above the Martian plains, nearly 3 times the height of Mount Everest. At its base, Olympus Mons is roughly the size of the entire state of Arizona, a gentle giant sleeping on a distant world. These 4 rocky worlds, Mercury, Venus, Earth, and Mars, are called the terrestrial planets, from the Latin word terra meaning earth or land. They share a common story, forged in the heat of the inner solar system, each one solid and dense, with thin atmospheres or no atmosphere at all. Let your breathing slow as we drift farther from the sun's warmth, beyond Mars, into a realm of ancient fragments. Here, between the orbits of Mars and Jupiter, lies a band of countless rocky remnants, the asteroid belt. This region stretches across millions of kilometers of space, a bridge between the inner rocky worlds and the outer giants. Despite what you might imagine from movies and stories, the asteroid belt is mostly empty space. If you were to stand on one asteroid, you likely wouldn't even be able to see another with your naked eye. The asteroids are so spread out across such vast distances that spacecraft can fly through this region without much danger of collision. Yet collectively, these tumbling rocks tell an important story. They are the building blocks that never became a planet, fragments from the dawn of our solar system, preserved like cosmic fossils for 4.6 billion years. The largest object in the asteroid belt is Ceres, which is so massive, about 940 kilometers in diameter, that it's been reclassified as a dwarf planet. Ceres contains nearly 1/3 of the entire mass of the asteroid belt. Beneath its ancient, cratered surface, scientists believe there may be a subsurface ocean of liquid water, making this distant world another place where, perhaps, simple life might exist. Beyond the asteroid belt, we cross an invisible boundary. This is where the young sun's heat could no longer prevent lighter elements from condensing. Here, water could freeze into ice, and gases could cling together. This is the realm of the gas giants, and the first world we encounter is the king of planets, Jupiter. Jupiter is truly immense, so enormous that 1,300 Earths could fit inside its volume. This giant world contains more mass than all the other planets in our solar system combined. If you could place every planet, moon, asteroid, and comet except Jupiter on one side of a cosmic scale, Jupiter alone would outweigh them all. Despite its size, Jupiter spins faster than any other planet, completing one rotation in just under 10 hours. This rapid rotation causes Jupiter's clouds to stretch into bands of swirling colors, creams, oranges, reds, and browns, creating the beautiful striped appearance we see through telescopes. The most famous feature on Jupiter is the Great Red Spot, a storm so vast that 2 or 3 Earths could fit inside it. This anticyclonic hurricane has been raging for at least 350 years, possibly much longer. Astronomers first observed it through telescopes in the 1600s, and it continues spinning today, though it has been slowly shrinking over the past century. Winds at the edges of this storm reach speeds of 400 kilometers per hour, yet the storm maintains its coherent structure decade after decade, a testament to the strange physics of this giant world. Jupiter serves as a guardian of the inner solar system. Its powerful gravity acts like a cosmic vacuum cleaner, attracting comets and asteroids that might otherwise threaten Earth. Many potentially dangerous objects have been pulled into Jupiter or flung out of the solar system entirely by this giant's gravitational influence, making Jupiter, in a very real sense, a protector of life on Earth. As you relax even deeper, imagine drifting farther into the outer reaches of our solar system. Beyond Jupiter, we encounter perhaps the most beautiful sight in all the solar system, Saturn, the jewel of our cosmic neighborhood. Saturn is the second largest planet, a gas giant adorned with the most spectacular ring system known to humanity. When Galileo first pointed his primitive telescope at Saturn in 1610, he couldn't quite make out what he was seeing. The rings appeared to him as strange bulges on either side of the planet, mysterious ears that sometimes seemed to disappear. It wasn't until 1655 that Dutch astronomer Christian Huygens, with a more powerful telescope, realized Saturn was encircled by a flat ring. What appeared to be one ring is actually thousands upon thousands of individual ringlets, like grooves on a cosmic record. These magnificent rings stretch out more than 280,000 kilometers from one edge to the other. That's about 3/4 of the distance from Earth to the Moon. Yet despite their vast width, the rings are remarkably thin, averaging only about 10 meters thick in most places. If you could shrink Saturn's rings down to the size of a football field, they would be thinner than a sheet of paper. They're composed of countless chunks of water, ice and rock, ranging in size from tiny grains like sugar to pieces as large as houses or mountains, all orbiting Saturn in an intricate dance. Scientists believe Saturn's rings are relatively young in cosmic terms, perhaps only 100 to 400 million years old. This means the rings formed long after the dinosaurs first walked on Earth, possibly from a moon that ventured too close to Saturn and was torn apart by the planet's gravity, or from a comet that shattered when it passed too near. Like Jupiter, Saturn is a gas giant with no solid surface to stand on. If you could somehow survive the crushing pressure and extreme cold, and you descended through Saturn's atmosphere, you would fall for thousands of kilometers through layers of hydrogen and helium gas that gradually compress into liquid, then into exotic metallic forms deep within. Saturn is so light for its size that its average density is less than water. If you could find an ocean large enough, Saturn would float. Saturn spins rapidly on its axis, completing one rotation in just over 10.5 hours. This fast rotation, combined with its gaseous composition, causes Saturn to bulge noticeably at its equator. The planet is about 10% wider at its equator than it is from pole to pole, giving it a slightly flattened appearance, like a ball that's been gently squeezed from top and bottom. But Saturn's wonders extend beyond the planet itself. This giant world is attended by a court of at least 146 known moons, each one a world unto itself. The largest, Titan, is bigger than the planet Mercury and is the only moon in our solar system with a thick atmosphere. Beneath Titan's hazy orange skies, liquid methane and ethane rain down and collect in lakes and seas, the only place besides Earth where we've found stable liquid on a world surface, though here the liquid is not water but hydrocarbons, eerily similar to the natural gas we use on Earth. Let yourself drift even farther now, into the cold, dark reaches of the outer solar system where sunlight becomes faint and the worlds take on an ethereal, ghostly quality. Here we find the ice giants, Uranus and Neptune, worlds so distant that they exist in perpetual twilight. Uranus is perhaps the strangest planet in our solar system, a world that seems to have forgotten how planets should behave. While all the other planets spin roughly upright like tops, Uranus rotates on its side, tilted over at an angle of 98 degrees. Imagine Earth lying on its side as it orbits the Sun, with one pole pointing directly at our star for years at a time, then the other pole taking its turn. This is how Uranus moves through space. Scientists believe that early in the solar system's history, Uranus suffered a catastrophic collision with another planet-sized body, a cosmic impact so violent it knocked the planet onto its side, where it has remained for billions of years. This unusual tilt creates the most extreme seasons in the solar system. Each pole of Uranus experiences 42 years of continuous sunlight, followed by 42 years of complete darkness. A single year on Uranus lasts 84 Earth years, so if you were born during Uranus's spring, you would be an elderly person before you saw your first Uranian summer. Despite being the third largest planet, Uranus appears as a pale, serene blue-green disk with few visible features. This tranquil appearance comes from methane in its atmosphere, which absorbs red light and reflects blue and green wavelengths back into space. The planet's upper atmosphere is the coldest in the solar system, with temperatures plunging to -224 degrees Celsius, cold enough to freeze carbon dioxide, the gas we breathe out, into dry ice. Uranus has a faint ring system of its own, discovered only in 1977, made of the darkest particles in the solar system, chunks so dark they reflect almost no light at all, like pieces of charcoal orbiting in the darkness. The planet is also attended by 27 known moons, uniquely named not after Greek or Roman gods, but after characters from the works of William Shakespeare and Alexander Pope. Titania, Oberon, Puck, and Ariel dance around this sideways world. Beyond Uranus, at the edge of the planetary realm, lies Neptune, the last of the major planets. Neptune is so far from Earth, about 4.5 billion kilometers, that it took the Voyager 2 spacecraft 12 years to reach it, and it remains the only spacecraft ever to visit this distant world. That flyby occurred in 1989, just once in all of human history. Neptune is a world of vivid, deep blue, even more intensely colored than Uranus. Like its neighbor, Neptune gets its striking color from methane in its atmosphere, but the deeper, richer blue suggests there's something else at work, some additional unknown compound that deepens the hue. This beautiful blue planet is home to the fastest winds in the solar system, storms with wind speeds reaching 2,100 kilometers per hour, faster than the speed of sound on Earth. These supersonic winds scream across Neptune's cloud tops in the near-absolute cold of deep space, driven by some internal heat source scientists still don't fully understand. Neptune has 16 known moons, the largest of which is Triton. Triton is unusual because it orbits Neptune in the opposite direction to the planet's rotation, a retrograde orbit. This tells scientists that Triton wasn't born alongside Neptune, but was captured by the planet's gravity long ago, perhaps stolen from the Kuiper Belt beyond. Triton is one of the coldest objects in the solar system, with surface temperatures of -235 degrees Celsius, yet it's geologically active, with nitrogen geysers erupting from beneath its icy crust, spraying plumes 8 kilometers high into the thin atmosphere. Breathe slowly and let yourself float into the deepest cold, beyond the realm of the giant planets, to a place where the sun appears as nothing more than a bright star among other stars. Here, in the outermost reaches, lies a vast ring of frozen worlds, the Kuiper Belt. The Kuiper Belt begins beyond Neptune's orbit and extends outward for billions of kilometers, a disc-shaped region containing hundreds of thousands of icy bodies, remnants from the birth of our solar system that never coalesced into planets. Like the asteroid belt between Mars and Jupiter, the Kuiper Belt is a collection of cosmic leftovers, but these objects are made primarily of frozen methane, ammonia, and water, ices that could never survive in the warmer inner solar system. Scientists estimate the Kuiper Belt contains more than 100,000 objects larger than 100 kilometers across, ancient time capsules preserving the chemistry of the early solar system. Among these countless frozen wanderers, one captured humanity's heart for decades, Pluto. Discovered in 1930 by astronomer Clyde Tombaugh, Pluto was considered the 9th planet for 76 years. This distant world is small, only about 2,380 kilometers in diameter, roughly 2/3 the size of Earth's moon. In 2006, when astronomers discovered many other objects in the Kuiper Belt similar in size to Pluto, they created a new classification, dwarf planets. Pluto became the prototype for this new category, joined by Eris, Makemake, Haumea, and Ceres from the asteroid belt. Yet Pluto's demotion shouldn't diminish its wonder. When NASA's New Horizons spacecraft flew past Pluto in 2015 after a journey of 9.5 years, it revealed a world of stunning complexity and beauty. Pluto's surface displays a heart-shaped region of frozen nitrogen called Tombaugh Regio, mountains of water ice reaching 3,500 meters high, as tall as the Rocky Mountains, and vast plains where nitrogen ice flows like glaciers across the landscape. The surface is young in geological terms, showing evidence of activity within the past few million years, suggesting that this tiny world, so far from the sun's warmth, still has some internal heat source keeping it alive. Pluto has 5 known moons, the largest being Charon, which is so large relative to Pluto, about half Pluto's diameter, that the two worlds orbit around a point in space between them. Some scientists consider Pluto and Charon a binary dwarf planet system, two partners locked in an eternal dance. Charon always shows the same face to Pluto, and Pluto always shows the same face to Charon. They're tidally locked to each other, each frozen in the other's gaze for all time. At Pluto's distance, the sun appears 1,000 times dimmer than it does from Earth. Noon on Pluto is like deep twilight on Earth, a perpetual dusk where the sun is merely the brightest star in a black sky. It takes sunlight more than 5.5 hours to reach Pluto. If you could somehow communicate instantly with someone on Pluto, and they looked up at the sun at that moment, they would be seeing light that left the sun before you began your conversation. beyond Pluto and the main Kuiper Belt lies something even more mysterious, the scattered disk, a region of space where objects follow highly elliptical, tilted orbits, as if they've been scattered by gravitational encounters with Neptune over billions of years. And farther still, perhaps beginning at 2,000 times Earth's distance from the Sun, scientists theorize there exists the Oort cloud, a vast spherical shell of trillions of icy objects surrounding our entire solar system like a cosmic bubble. These distant frozen wanderers are so far away that they're barely held by the Sun's gravity, yet they remain bound to our star, the most distant members of our solar system family. The Oort cloud is thought to extend halfway to the nearest star, Proxima Centauri. Objects here take millions of years to orbit the Sun just once, moving through the darkness in slow, patient paths that began when our solar system was young. Rest now as we turn our attention to the travelers, the wanderers that move through our solar system on long, graceful journeys, the comets. These ancient visitors have captured human imagination for thousands of years, appearing suddenly in our skies with their glowing heads and streaming tails, then vanishing back into the darkness. Comets are often called dirty snowballs, chunks of ice, rock, and frozen gases that spend most of their existence in the cold outer reaches of the solar system, in the Kuiper Belt or the distant Oort cloud. Some comets take only a few years to orbit the Sun, while others take millions of years to complete a single orbit, venturing out to the very edge of the Sun's gravitational influence before slowly falling back inward. When a comet's elliptical path brings it close to the Sun's warmth begins to work its magic. As a comet approaches the inner solar system, the ice on its surface begins to vaporize, turning directly from solid to gas without becoming liquid first, a process called sublimation. This releases dust and gas trapped within the ice, creating a glowing cloud around the comet's nucleus called a coma. The coma can grow to be enormous, sometimes larger than Jupiter, though it contains very little actual matter. It's mostly empty space with scattered particles. The Sun's radiation pressure and the solar wind then push this gas and dust away from the comet, creating the spectacular tail that can stretch for millions of kilometers across space. Interestingly, a comet's tail always points away from the Sun, regardless of which direction the comet is traveling. When a comet is moving toward the Sun, its tail streams behind it, but when the comet swings around the Sun and heads back out into deep space, the tail actually leads the way, pushed outward by the solar wind. Some bright comets even develop two tails, a blue ion tail made of charged particles, and a white dust tail made of tiny solid particles, each responding differently to the Sun's influence. The most famous comet is Halley's Comet, which returns to the inner solar system every 75 to 76 years. This comet has been recorded by human observers for more than 2,000 years, appearing in ancient Chinese, Babylonian, and European records. It last visited us in 1986 and won't return until 2061. When it does return, it will be the same ancient traveler that was witnessed by people throughout history, by those who built the pyramids, by medieval Europeans who saw it as an omen, and by Mark Twain, who was born during its 1835 appearance and died during its 1910 return, having predicted this cosmic coincidence. As comets journey through the inner solar system again and again, they leave behind trails of dust and small particles along their orbital paths. When Earth passes through these debris trails in its orbit around the Sun, these particles enter our atmosphere at tremendous speeds, up to 70 kilometers per second, and burn up in bright streaks we call meteors or shooting stars. The particles themselves, while still in space, are called meteoroids. Most are no larger than grains of sand, yet they create brilliant flashes of light as they vaporize in the upper atmosphere, typically between 80 and 120 kilometers above Earth's surface. Several times each year, Earth passes through particularly dense comet debris trails, creating meteor showers that can produce dozens or even hundreds of visible meteors per hour. The Perseid meteor shower in August comes from the debris trail of Comet Swift-Tuttle, while the Geminid shower in December originates from an asteroid called Phaeton. During these showers, if you lie on your back and look up at a dark sky, you can watch the ancient dust from comets burn up in real time, each brief flash representing a tiny piece of our solar system's history meeting its end in a moment of beauty. Sometimes, larger chunks of space rock survive the fiery passage through Earth's atmosphere and reach the ground. These are called meteorites, and they're remarkably valuable to science. Meteorites are the oldest rocks you can hold in your hand, samples of the solar system from before Earth even existed, carrying within them the chemical signatures of the nebula from which everything formed. Let us return now to the heart of our solar system, to the source of warmth and light that makes everything else possible, our sun. Close your eyes and feel its warmth on your face, even now, as we explore the magnificent star that anchors our cosmic home. The Sun is a medium-sized star, what astronomers classify as a G-type main sequence star, or G2V. It may seem impossibly large to us. You could fit 1.3 million Earths inside the Sun's volume, but in the grand scale of the universe, our Sun is quite average. There are stars hundreds of times larger, and stars much smaller. Our Sun is, in many ways, perfectly ordinary, and that ordinariness is part of what makes it special. It's stable, reliable, and just the right size to burn steadily for billions of years. The Sun is approximately 4.6 billion years old, born from the same collapsing cloud of gas and dust that formed the rest of the solar system. It's currently in the middle of its life, what astronomers call the main sequence phase. The Sun has enough hydrogen fuel to continue shining steadily for another 5 billion years. When that fuel finally runs low, our star will enter its old age, swelling into a red giant so large it will likely engulf Mercury, Venus, and possibly Earth, before finally shedding its outer layers and collapsing into a white dwarf, a dense, Earth-sized ember that will slowly cool over trillions of years. But for now, the Sun burns brightly, converting 600 million tons of hydrogen into helium every single second through nuclear fusion in its core. The core of the Sun is unimaginably hot, about 15 million degrees Celsius, and under such tremendous pressure that hydrogen atoms are forced together with enough energy to overcome their natural repulsion and fuse into helium. This fusion process releases enormous amounts of energy in the form of gamma-ray photons. Here's something remarkable. A photon of light created in the Sun's core doesn't immediately fly out into space. Instead, it begins a journey that can take between 100,000 and 200,000 years. The inside of the Sun is so dense with matter that the photon constantly bounces off atoms, traveling in a random zigzag path called a random walk, gradually working its way from the core outward. A photon might travel a few millimeters before hitting another particle, changing direction, traveling another tiny distance, hitting another particle over and over, millions upon millions of times. By the time that photon finally reaches the Sun's surface and flies off into space, the journey to Earth takes only 8 minutes and 20 seconds. But the light you see from the sun today actually began its journey from the core before humans existed. The visible surface of the sun, what we see when we look up, is called the photosphere, and it has a temperature of about 5,500 degrees Celsius. This may seem cooler than you'd expect for the surface of a star, but it's still hot enough to vaporize any known material instantly. The photosphere isn't a solid surface but rather the layer where the sun's gases finally become thin enough that light can escape into space. Above the photosphere lies the sun's atmosphere. The lowest layer is called the chromosphere, which glows with a reddish color visible during solar eclipses. Above that lies the corona, the sun's outer atmosphere, which extends millions of kilometers into space. Here's one of the sun's greatest mysteries. While the photosphere sits at 5,500 degrees Celsius, the corona is somehow heated to millions of degrees, more than 2 million degrees Celsius in some regions. This defies our everyday experience, like a light bulb surface being cool while the air around it is scorching hot. Scientists are still working to fully understand how the corona becomes so hot. The sun isn't perfectly smooth and calm. Its surface is constantly churning with activity. Sunspots appear as dark patches on the photosphere, regions that are slightly cooler than their surroundings, around 3,800 degrees Celsius, which makes them appear dark by contrast. These sunspots are caused by intense magnetic fields that prevent heat from flowing to the surface. Some sunspots grow large enough to swallow Earth whole. The number of sunspots rises and falls in a predictable cycle lasting approximately 11 years, called the solar cycle. During solar maximum, the sun's surface can be covered with numerous sunspot groups, while during solar minimum, weeks can pass without a single visible spot. As you sink deeper into relaxation, imagine the sun not as a static ball of fire, but as a living, breathing presence, constantly sending out streams of energy that touch every corner of our solar system. The sun's influence extends far beyond its visible surface, carried on invisible winds that flow through space. The solar wind is a continuous stream of charged particles, mostly electrons and protons, that flows outward from the sun in all directions at speeds between 400 and 800 kilometers per second. This wind originates from the sun's corona, where temperatures are so extreme that particles gain enough energy to escape the sun's gravitational pull entirely. Every second, the sun loses about 1.5 million tons of material to the solar wind, though this is such a tiny fraction of the sun's total mass that it could continue at this rate for billions of years without significantly diminishing our star. The solar wind doesn't stop at any planet, it continues outward, creating an enormous bubble around the entire solar system called the heliosphere. This bubble extends more than 18 billion kilometers from the sun, far beyond Pluto, to a boundary called the heliopause. At this distant frontier, the solar wind finally slows down and mingles with the interstellar medium, the gas and dust between the stars. The heliopause marks the true edge of the sun's domain, the boundary between our solar system and interstellar space. In 2012, NASA's Voyager 1 spacecraft became the first human-made object to cross this boundary, and in 2018, Voyager 2 followed, both craft carrying humanity's message into the space between the stars. Sometimes the sun releases its energy more violently. Solar flares are sudden, intense bursts of radiation that erupt from the sun's surface, releasing as much energy as millions of nuclear bombs in just a few minutes. These flares occur when magnetic field lines near sunspots suddenly reconnect, releasing tremendous amounts of stored magnetic energy. The radiation from a powerful solar flare can reach Earth in just 8 minutes, traveling at the speed of light. Even more dramatic are coronal mass ejections, or CMEs. These are massive bubbles of plasma and magnetic field that erupt from the sun's corona and hurtle into space, carrying billions of tons of solar material. When a CME is directed toward Earth, it can take 1 to 3 days to arrive. If it strikes Earth's magnetic field, it can trigger a geomagnetic storm, a disturbance in Earth's magnetosphere that can affect satellites, radio communications, and power grids. But these solar storms also create one of nature's most beautiful displays, the aurora. Earth is surrounded by an invisible magnetic field, generated by the churning of molten iron in our planet's outer core. This magnetic field extends thousands of kilometers into space, creating a protective shield called the magnetosphere that deflects most of the solar wind around our planet, like a rock in a stream causing water to flow around it. When charged particles from the solar wind or a CME interact with Earth's magnetosphere, some particles are funneled down along the magnetic field lines toward the polar regions. These particles collide with oxygen and nitrogen molecules in Earth's upper atmosphere, typically between 100 and 300 kilometers above the surface. The collisions transfer energy to these atmospheric molecules, which then release that energy as light, creating the shimmering, dancing curtains of color we call the aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. The colors of the aurora tell us which atmospheric gases are being excited. Oxygen produces green light, the most common aurora color, when struck at lower altitudes, and rare red auroras when struck at higher altitudes above 300 kilometers. Nitrogen produces blue and purple hues. The auroras shift and dance because the solar wind is constantly changing, strengthening and weakening, causing the curtains of light to ripple and wave like silk banners in a celestial breeze. During powerful geomagnetic storms, auroras can be seen much farther from the poles than usual. The Great Geomagnetic Storm of 1859, known as the Carrington Event, was so powerful that auroras were visible as far south as the Caribbean, and telegraph systems around the world sparked and caught fire. In our modern, technology-dependent world, a storm of that magnitude could cost trillions of dollars in damage to satellites, power grids, and electronic systems, a reminder that we live within our sun's atmosphere, connected to our star in ways both beautiful and potentially dangerous. Let your mind drift now to the companions of planets, the moons that orbit their parent worlds in silent devotion. Our solar system is home to more than 290 known moons, each one a world unto itself, and we'll begin with the one most familiar to us, Earth's moon. Our moon is the 5th largest moon in the solar system, with a diameter of 3,474 kilometers, about 1/4 the size of Earth. This makes our moon unusually large compared to its planet. Most moons are much smaller relative to their parent worlds. The moon is so large and so close, an average of 384,400 kilometers away, that it creates significant tides in Earth's oceans through its gravitational pull, causing the seas to rise and fall in a rhythm that has shaped coastal life for billions of years. The moon wasn't always our companion. Scientists believe the moon formed about 4.5 billion years ago, shortly after Earth itself, in a catastrophic collision. A Mars-sized body called Theia struck the young Earth in a glancing blow, and the impact was so violent that it vaporized rock and sent enormous amounts of debris into orbit around Earth. This debris gradually coalesced over time, cooling and combining to form the Moon. This means the Moon is partly made from Earth itself. We and our lunar companion share the same ancient material. The Moon is gradually moving away from Earth at a rate of about 3.8 centimeters per year, roughly the same speed your fingernails grow. Billions of years ago, the Moon was much closer, looming much larger in Earth's sky and creating far more dramatic tides. As the Moon moves away, it slowly steals rotational energy from Earth through tidal interactions, which gradually lengthens our day. When the Moon first formed, an Earth day may have been only 5 to 6 hours long. The Moon's gradual retreat will continue, but even billions of years from now, it will still be visible in our sky, just smaller and more distant. The Moon is tidally locked to Earth, meaning it rotates on its axis at exactly the same rate it orbits Earth, which takes 27.3 days. This synchronization means the same face of the Moon, the near side, always points toward Earth. We never see the far side from Earth, though it's been extensively photographed by spacecraft. There is no permanent dark side of the Moon. Both the near and far sides experience roughly 2 weeks of sunlight followed by 2 weeks of darkness as the Moon orbits Earth. Beyond Earth, the solar system's moons become even more fascinating. Jupiter's moon Io is the most volcanically active body in the entire solar system, with hundreds of active volcanoes covering its surface. These aren't volcanoes like those on Earth, which erupt molten rock. Io's volcanoes erupt fountains of sulfur and sulfur dioxide that shoot hundreds of kilometers into space. Io's intense volcanic activity is caused by tidal heating, Jupiter's immense gravity, along with gravitational tugs from other nearby moons, constantly squeezes and flexes Io's interior, generating tremendous friction and heat, keeping the Moon's interior molten despite being so far from the Sun. Another of Jupiter's moons, Europa, may be one of the best places to search for life beyond Earth. Europa's surface is covered by a thick shell of water ice, crisscrossed with long cracks and ridges. Beneath this frozen crust, scientists believe there exists a global ocean of liquid water, possibly 100 kilometers deep, containing more water than all of Earth's oceans combined. This subsurface ocean is kept liquid by tidal heating from Jupiter, similar to what powers Io's volcanoes but less extreme. Where there's liquid water, warmth, and possibly volcanic vents on the ocean floor providing energy and nutrients, there's the possibility of life. Saturn's moon Enceladus also harbors a subsurface ocean beneath its icy exterior. What makes Enceladus particularly exciting is that the Moon actively sprays water into space through enormous geysers at its south pole. These plumes shoot hundreds of kilometers high, and spacecraft have flown through them, detecting water vapor, ice particles, salts, and even organic molecules. The presence of these materials suggests that Enceladus's ocean is in contact with a rocky seafloor, creating conditions that might support microbial life. The ice particles from these geysers supply material to Saturn's E-ring, creating a gossamer band of ice that encircles the planet. Miranda, one of Uranus's moons, has perhaps the most dramatic and puzzling surface in the solar system. Its landscape is a chaotic jumble of different terrains, smooth plains next to regions carved by deep canyons and ridges. One feature, called Verona Rupes, is the tallest known cliff in the solar system, dropping about 20 kilometers down, nearly 13 miles. If you fell from the top of this cliff on Miranda, where gravity is much weaker than Earth's, you would fall for approximately 12 minutes before finally hitting the ground, a long, dreamlike descent through the pale light of distant Uranus. Rest now as we contemplate the invisible forces that hold our solar system together, the gentle but inexorable pull of gravity that choreographs the cosmic dance of worlds. Everything in our solar system moves according to gravity's ancient rhythm, from the smallest grain of dust to the largest planet. Gravity is why planets orbit the Sun in ellipses rather than circles, a discovery made by Johannes Kepler in the early 1600s. Though we often think of orbits as circular for simplicity, every planet follows an elliptical path, with the Sun positioned at one of the two focal points of the ellipse. Some orbits, like Venus's, are very nearly circular, while others, like Mercury's, are noticeably elongated. This means that planets are sometimes closer to the Sun and sometimes farther away as they complete their yearly journeys. Earth's orbit, for example, isn't perfectly circular. We're actually closest to the Sun, a point called perihelion, in early January, when we're about 147 million kilometers away. We're farthest from the Sun, at aphelion, in early July, at about 152 million kilometers. This might seem counterintuitive since the Northern Hemisphere experiences winter during perihelion, but Earth's seasons are caused by the tilt of its axis, not its distance from the Sun. The 5 million kilometer difference in distance has far less effect on temperature than the angle at which sunlight strikes the Earth. The speed at which planets orbit the Sun follows a beautiful mathematical relationship discovered by Kepler. Planets closer to the Sun move faster, while those farther away move more slowly. Mercury races around the Sun at an average speed of 47 kilometers per second, while Neptune plods along at just 5.4 kilometers per second, nearly 9 times slower. This is why Mercury's year is only 88 days while Neptune takes 165 Earth years to complete one orbit. Orbital resonances create some of the most elegant patterns in the solar system. A resonance occurs when two orbiting bodies exert regular, periodic gravitational influence on each other, usually because their orbital periods form a simple numerical ratio. For instance, Neptune and Pluto are locked in a 3:2 resonance. For every 3 orbits Neptune completes, Pluto completes exactly 2. This resonance has kept their orbits stable for billions of years and ensures that even though their paths cross on paper, Pluto and Neptune will never collide. Jupiter's moons Ganymede, Europa, and Io are locked in an even more elegant resonance pattern called a Laplace resonance. For every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This 1:2:4 pattern creates a gravitational symphony that has remained stable for billions of years, with each moon's gravity tugging on the others in a perfectly coordinated rhythm. The same gravitational forces that govern orbits also explain why large celestial bodies are round. When an object in space has enough mass, generally anything with a diameter larger than about 400 to 600 kilometers, its own gravity becomes strong enough to pull it into a spherical shape. This is why planets and large moons are round, while smaller asteroids and comets can be irregular, potato-shaped objects. Gravity pulls equally in all directions toward the center of mass, and a sphere is the shape that best satisfies this equal pull from all sides. But gravity does more than shape orbits and bodies, it also stretches space itself. According to Einstein's general relativity, massive objects like the Sun actually warp the fabric of spacetime around them, creating curves and valleys in space. Planets don't orbit the sun because they're being pulled by an invisible force. Instead, they're following the straightest possible path through curved spacetime, like a marble rolling along the surface of a stretched rubber sheet with a bowling ball in the center. The more massive an object, the more it curves spacetime, and the stronger its gravitational effects. This warping of spacetime is subtle for objects like Earth. You'd need incredibly precise instruments to detect it, but it becomes dramatic near very massive or dense objects. Near the Sun, spacetime is curved enough that light itself bends as it passes by, an effect that was famously confirmed during a solar eclipse in 1919, proving Einstein correct. If you could somehow stand on the surface of a neutron star, the collapsed core of a dead massive star, spacetime would be so warped that time itself would flow noticeably slower for you than for someone far away in flat space, and the gravity would be so strong it would instantly crush you into a layer of atoms only a few nanometers thick. The solar wind doesn't blow uniformly in all directions. It's shaped by the sun's magnetic field, which extends outward and rotates with the sun. Because the sun rotates, the magnetic field lines spiral outward like water from a rotating sprinkler, creating a pattern called the Parker spiral. This means that solar wind particles don't travel straight outward from the sun, but follow these spiral magnetic field lines. The effect becomes more pronounced farther from the sun, so by the time the solar wind reaches Earth, it's approaching from a slight angle rather than directly from the sun. Earth has 2 points in its orbit where day and night are nearly equal in length all over the planet. These are called the equinoxes. The vernal equinox occurs around March 20th, marking the beginning of spring in the northern hemisphere, while the autumnal equinox occurs around September 22nd. On these days, the sun rises due east and sets due west for observers everywhere on Earth, and the sun shines directly on the equator. The word equinox comes from Latin, meaning equal night, though the day is actually slightly longer than the night even on the equinox due to atmospheric refraction bending sunlight around Earth's curve. The outer solar system may harbor a yet undiscovered planet, sometimes called Planet 9 or Planet X. Astronomers have noticed that certain distant Kuiper Belt objects have strangely clustered orbits, all tilted and aligned in a way that seems statistically unlikely unless something massive is gravitationally shepherding them. Computer models suggest there might be a planet about 5 to 10 times Earth's mass orbiting between 400 and 800 Australian dollars from the Sun. If this planet exists, it would take 10,000 to 20,000 years to complete one orbit. Astronomers are actively searching for this hypothetical world, though the vast area of sky to search and the extreme faintness of such a distant object make it extraordinarily difficult to find. Earth's axis is tilted at 23.5 degrees relative to its orbital plane around the Sun, and this tilt is responsible for our seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer with longer days and more direct sunlight, while the southern hemisphere experiences winter. 6 months later, the situation reverses. Without this axial tilt, there would be no seasons. Every location on Earth would experience the same weather conditions year-round, and the poles would remain in eternal twilight, never seeing the sun rise high in the sky. Jupiter emits more energy than it receives from the Sun. The planet radiates about 1.6 times as much heat as it absorbs from solar radiation. This extra energy comes from the slow gravitational contraction of the planet. Jupiter is still very gradually shrinking, compressing under its own immense gravity, and this compression generates heat. In essence, Jupiter is still cooling down from its formation 4.6 billion years ago, like a dying ember that retains warmth long after the fire has gone out. Saturn's rings are not solid, They're made up of countless individual particles, each orbiting Saturn independently. The particles range from tiny grains the size of sugar crystals to chunks as large as houses. If you could somehow stand in Saturn's rings, you wouldn't feel like you were standing on anything solid. Instead, you'd see particles slowly drifting past you in all directions, each following its own orbital path. The rings are so thin relative to their width that if you made a scale model where the rings were as thin as tissue paper, they would be over a kilometer across. Mars has the largest dust storms in the solar system. During certain times in the Martian year, dust storms can grow to engulf the entire planet, blocking out the sun completely for weeks or months. These global dust storms are powered by solar heating and can lift dust particles up to 60 kilometers into the atmosphere. The 2018 global dust storm was so intense that it blocked sunlight from reaching NASA's Opportunity rover's solar panels, ultimately ending the mission after nearly 15 years of exploration. The sun's gravity is strong enough to influence objects at incredible distances. The edge of the sun's gravitational sphere of influence, called the Hill sphere, extends about 2 light-years from the sun, or roughly halfway to the nearest star. This means the sun's gravity can, in theory, hold objects in orbit at distances far beyond even the Oort cloud. However, at such extreme distances, the gravitational pull becomes so weak that even the slight gravitational influence of passing stars can perturb objects and potentially send them drifting away into interstellar space. Neptune has the most violent weather of any planet in our solar system relative to the energy it receives from the sun. Despite being the coldest planet and receiving 900 times less sunlight than Earth, Neptune has winds that exceed 2,000 kilometers per hour. Scientists believe this extreme weather is driven primarily by heat from Neptune's interior rather than from the sun, suggesting the planet has a powerful internal heat source, possibly from its formation or from ongoing chemical reactions in its interior layers. Earth is the densest planet in the solar system, with an average density of 5.52 grams per cubic centimeter. This high density comes from Earth's large iron core, which makes up about 1/3 of the planet's mass. In comparison, Saturn has an average density of only 0.687 grams per cubic centimeter, less than water. If you could place all the planets in a cosmic swimming pool, Saturn would float while all the others would sink. The gap in Saturn's rings, known as the Cassini division, is about 4,800 kilometers wide, wider than the distance across the United States. This gap appears dark because it contains far fewer ring particles than the surrounding regions. The Cassini division is caused by a gravitational resonance with Saturn's moon Mimas. Particles orbiting in the division would orbit Saturn exactly twice for every orbit of Mimas, and this resonance destabilizes their orbits, gradually clearing out the gap over millions of years. Ganymede, Jupiter's largest moon, is the biggest moon in the entire solar system. With a diameter of 5,268 kilometers, Ganymede is larger than the planet Mercury. If Ganymede orbited the Sun instead of Jupiter, it would easily be classified as a planet. Beneath its icy surface, Ganymede is believed to have a subsurface ocean containing more water than all of Earth's oceans. Remarkably, Ganymede is the only moon in the solar system known to have its own magnetic field, generated by a liquid iron core deep within, making it more planet-like than many actual planets. The Sun contains 99.86% of all the mass in the solar system, but it contains less than 1% of the solar system's angular momentum, the rotational energy of spinning and orbiting objects. Most of the angular momentum is carried by the planets, especially Jupiter, which, despite containing only about 0.1% of the solar system's mass, accounts for approximately 60% of the angular momentum. This distribution is one of the fundamental constraints that theories of solar system formation must explain. Earth's magnetic field has reversed many times throughout its history. The north and south magnetic poles have swapped positions hundreds of times over the past hundreds of millions of years, with reversals occurring irregularly, sometimes every few 100,000 years, sometimes waiting millions of years. We know this from studying ancient rocks that preserve the direction of Earth's magnetic field when they formed. Currently, the North Magnetic Pole is moving across the Canadian Arctic toward Russia at about 55 kilometers per year, much faster than its historical average. Scientists don't know exactly when the next reversal will occur, but geological evidence suggests we may be overdue. Phobos, one of Mars's two small moons, is slowly spiraling inward toward Mars. Tidal forces from Mars are gradually slowing Phobos's orbit, causing the moon to drop closer to the planet by about 1.8 centimeters per year. In approximately 50 million years, Phobos will either crash into Mars's surface or, more likely, be torn apart by tidal forces when it crosses the Roche limit, the distance at which Mars's gravity will overcome Phobos's own gravity. When this happens, Phobos will be shredded into a ring of debris that will orbit Mars for a few million years before gradually raining down onto the planet's surface. The solar system passes through different regions of the Milky Way galaxy as it orbits the galactic center. Our solar system takes approximately 230 million years to complete one orbit around the center of the galaxy, a period sometimes called a galactic year or cosmic year. The last time the solar system was in its current position in the galaxy, dinosaurs were just beginning to emerge on Earth. As we orbit, we occasionally pass through the spiral arms of the galaxy, regions with higher stellar density where more stars are forming. Some scientists have speculated that these passages might increase the rate of comet impacts on Earth, though this remains controversial. Io's surface is constantly being resurfaced by volcanic activity, so much so that Io has the youngest surface of any object in the solar system. The Moon's entire surface is replaced approximately once every million years through continuous volcanic eruptions. This means that any impact craters that form on Io are quickly buried under fresh lava flows, leaving Io's surface remarkably smooth and crater-free despite being billions of years old. Venus has more volcanoes than any other planet in the solar system. Over 1,600 major volcanoes have been identified on its surface, and there may be 1 million or more smaller ones. Some scientists believe that Venus undergoes periodic global resurfacing events every few 100 million years, where massive volcanic eruptions completely renew the planet's surface. The last such event may have occurred about 500 million years ago, which would explain why Venus's surface appears relatively young with few impact craters. The temperature difference between the sunlit and dark sides of Mercury is the most extreme in the solar system. On the side facing the Sun, temperatures can reach 430 degrees Celsius, hot enough to melt lead, while on the night side, temperatures plunge to -180 degrees Celsius. This 610-degree temperature difference exists because Mercury has almost no atmosphere to distribute heat around the planet, and its slow rotation means each side spends a long time in sunlight or darkness. Finally, the solar system is ancient, but it won't last forever in its current form. In about 5 billion years, when the Sun exhausts its hydrogen fuel and swells into a red giant, it will engulf and destroy Mercury and Venus. Earth may survive, though it will be baked sterile by the intense heat, its oceans boiled away into space. The outer planets will receive more heat and light than they do now. Moons like Europa and Enceladus might briefly become warm enough for their subsurface oceans to reach the surface. Eventually, the Sun will shed its outer layers as a planetary nebula, leaving behind a white dwarf core. The remaining planets, if any survive, will orbit this slowly cooling ember in the darkness of space, a solar system transformed but still bound together by gravity. And so our journey ends where all good journeys should, with wonder, with questions yet to be answered, and with the comfort of knowing that even as you rest, these worlds continue their ancient dance through the darkness, patient and eternal, waiting for us to return and explore them further. Our solar system is just one among hundreds of billions of star systems in the Milky Way galaxy, and the Milky Way is just one among hundreds of billions of galaxies in the observable universe. Yet this small corner of space, this collection of one ordinary star and its family of worlds, is home, the only place in the vast cosmos where we know life exists, where stories are told, where minds wonder about the universe and dream of distant stars. The solar system is vast, but it is ours to discover, one fact at a time. Sleep well, beneath the light of distant worlds.